Linear algebra for machine learning, scalars, vectors, and basic operations. Nova begins at the gate of the vector city with only a single number in hand. Historically, algebra grew from counting and measuring. Linear algebra begins when those numbers are arranged so position carries meaning. This chapter is the origin story. One value becomes a list becomes a space, and the viewer learns that shape is destiny. A scalar is one number. The code panel shows 3 AI scalars. Learning rate controls optimizer step size. Temperature controls generation randomness. And batch size controls how many examples move together. Real-world analogy. Think of a scalar like one dial on a coffee machine. A tiny turn can make the whole result stronger, weaker, hotter, or cooler. A vector is a list where order matters. Location uses latitude, longitude, and elevation. Medical readings add matched positions. So blood pressure adds to blood pressure, heart rate to heart rate, and temperature to temperature. Real-world analogy. A vector is like an address form where each box has a fixed label. Swapping postcode and street number would make the address wrong. Scalar multiplication uses one number to scale the whole vector. 3 times the recipe for 4 gives the recipe for 12. Every ingredient is multiplied by 3. Real-world analogy. It works like resizing a recipe for a larger dinner party. Every ingredient grows by the same multiplier. Basis vectors are the building blocks of a vector space. The vector 3, 7 is 3 copies of E1 plus 7 copies of E2. Dimension is the number of independent basis directions. Real-world analogy. A basis is like a city grid of east, west, and north-south streets. Any destination can be described by combining those independent directions. Linear algebra for machine learning. Dot products and orthogonal vectors. The arena opens with 2 directions facing each other. The dot product exists because people needed one number for alignment, work, cost, and similarity. It multiplies matching components because only matching meanings should interact. Orthogonality is the first defensive technique. Separate directions so information does not leak. The dot product multiplies matching entries and adds the results. Prices dot quantities gives one scalar, the total grocery bill. Real-world analogy. It is like a shopping receipt. Each item price meets its quantity, and the final sum is the bill. A neural network neuron uses the same operation. Weights say how important each input feature is. Inputs provide the current values, and the bias shifts the final score. Real-world analogy. A neuron is like a hiring scorecard. Each feature gets a weight. The scores are added, and the bias is the default tilt before the decision. Orthogonal vectors have dot product 0. The products cancel exactly, so knowing one direction tells you nothing about the other. PCA, QR decomposition, and stable initialization all rely on this independence. Real-world analogy. Orthogonal directions are like north-south and east-west streets. Moving along one does not move you along the other. Linear algebra for machine learning. Matrices and matrix operations. The battlefield expands from arrows to tables. Matrices became central because real systems have many entities and many features at once. Roots by times, samples by measurements, tokens by embeddings. Operations are not symbol tricks. They are rules for combining tables without losing the meaning of rows and columns. A matrix is a table with row and column meaning. Addition requires the same shape and combines matching addresses, which is why bias addition and residual connections work cleanly. Real-world analogy. Matrix addition is like adding 2 spreadsheets with the same layout. Monday sales add to Monday sales, not to Tuesday stock. Matrix multiplication uses dot products between rows and columns. The shared inner dimension must match. In Python, the @ symbol means matrix multiplication, while star usually means element-wise multiplication. Real-world analogy. It is like matching a kitchen's ingredient needs against supplier price lists to compute every possible order cost. The Hadamard product multiplies matching cells independently. That is why gates, dropout masks, and attention masks can keep or erase values position by position. Real-world analogy. Hadamard multiplication is like applying a sticker sheet to matching boxes. Each sticker affects only the cell underneath it. Transpose swaps rows and columns, and trace sums the diagonal of a square matrix. The transpose reverses transformation direction in backprop, while trace keeps derivative formulas compact. Real-world analogy. Transpose is like rotating a spreadsheet so rows become columns, while trace checks the diagonal of a seating chart where person and seat line up. Linear algebra for machine learning. Identity, inverse, pseudo-inverse, determinants, and spaces. Nova reaches the chamber of reversal, where some transforms can be undone and others crush information forever. Identity, inverse, determinant, column space, and null space answer one question from different angles. What survives the transformation, and what can never be recovered? The identity matrix leaves vectors unchanged. An inverse matrix undoes a square full rank matrix. For a 2x2 matrix, the determinant ad -bc must be non-zero before the inverse formula is valid. Real-world analogy. Identity is a clear glass pane, and an inverse is the matching undo button for a reversible machine. The pseudo-inverse handles rectangular or rank-deficient cases. In the worked example, 3 conflicting equations for one unknown become a least squares solution, the mean value 4. Real-world analogy. The pseudo-inverse is like finding the best compromise route when no exact road reaches the destination. The determinant tells how area or volume scales. A determinant of 0 means the matrix collapses space and cannot be inverted. This matters in normalizing flows, Gaussian distributions, and stability checks. Real-world analogy. The determinant is like watching a rubber stamp stretch or collapse. If the stamp flattens to a line, information has been lost. Column space is the set of outputs a matrix can produce. Null space is the set of inputs mapped to 0. Rank plus nullity equals the number of columns, linking preserved and destroyed information. Real-world analogy. Column space is the set of places an escalator can carry you, while null space is the luggage it crushes down to nothing. Linear algebra for machine learning. Vector norms and unit vectors. The hero now needs a ruler. Norms came from geometry, physics, and optimization because models need to know how big a vector is before they can compare, constrain, or safely update it. Unit vectors are compass bearings, pure direction without distance. Norm, magnitude, and length are different words for vector size. L2 measures Euclidean length. L1 sums absolute values and often encourages sparsity, and L infinity watches the largest component. Real-world analogy. Norms are different rulers, straight line distance, city block walking distance, and the single worst component. The vector 3, 4 has L2 norm 5. Dividing by 5 gives 0.6, 0.8, a unit vector that points the same way but has length 1. Real-world analogy. The 3, 4, 5 vector is the same geometry as a ladder leaning 3 meters out and 4 meters up the wall. Training code uses norms constantly. Weight normalization divides by a matrix or vector size. Gradient clipping rescales gradients that exceed max norm. And L infinity normalization limits every component. Real-world analogy. Training code uses norms like a speed limiter. If the update is too large, clip it before the model skids. Linear algebra for machine learning. Matrix norms and weighted quadratic norms. The ruler grows into a stress gauge for whole transformations. Matrix norms tell how much a matrix can energize, stretch, or destabilize a signal. Weighted quadratic norms enter like mission priorities. Not every error deserves the same punishment. The Frobenius norm treats the matrix as a grid of numbers and sums all squared entries. It appears in weight decay, matrix factorization, and low-rank approximation error. Real-world analogy. Frobenius norm is like measuring all lights on a control panel by adding the brightness from every bulb. The spectral norm asks for the maximum stretch over all unit input directions. Large spectral norms can amplify gradients and make models sensitive to adversarial perturbations. Real-world analogy. Spectral norm is the strongest setting on a pasta roller. It tells the largest stretch any dough direction can suffer. A weighted quadratic norm uses a matrix Q to say which errors matter most. If Q is the identity, it is ordinary squared L2 length. With a diagonal Q, each component gets its own priority. Real-world analogy. A weighted quadratic norm is like a hospital triage chart where a breathing error matters more than a typo on a form. Linear algebra for machine learning. Similarity, outer products, Kronecker products, and conditioning. This chapter is the strategy hall. Cosine similarity compares direction. Outer products build interaction maps. Kronecker product stamp structure at scale. And condition number warns when the floor is slippery. Together they turn raw matrix skills into engineering judgment. Cosine similarity divides the dot product by both vector norms, so it compares direction rather than magnitude. That is why embedding search often ranks by cosine similarity. Real-world analogy. Cosine similarity is like comparing two compasses after ignoring how far each person walked. The outer product creates a matrix of all pairwise products. It is the shape behind covariance estimates, rank 1 updates, and fully connected layer gradients. Real-world analogy. The outer product is like making a multiplication table between every worker and every task. The Kronecker product replaces each entry of A with that entry times the whole matrix B. This gives structured expansion used in KFAC optimizers, separable filters, and compact parameterizations. Real-world analogy. Kronecker product is like tiling a floor with repeated patterns, where each room scales the tile design differently. The condition number estimates sensitivity. A huge condition number means tiny input errors can become large output errors, so code should consider regularization, scaling, or SVD-based solves. Real-world analogy. Condition number is like checking whether a table is level before doing delicate work. A tiny bump can spill everything. Linear algebra for machine learning. Linear and geometric transformations. Nova steps into the transformation gate, where the same object can be described in many coordinate languages. Change of basis, projection, rotation, camera geometry, SO3, and orthogonal matrices explain why a model can move between views while preserving what matters. Change of basis keeps the vector but changes the coordinate language. The matrix P stores the new basis vectors as columns. Multiplying by P goes to standard coordinates. Multiplying by P inverse goes into the new basis. Real-world analogy. Change of basis is like giving the same location in street addresses, GPS coordinates, or subway stops. A projection matrix keeps the component of a vector inside a subspace. P squared equals P because projecting twice gives no further change. Real-world analogy. Projection is like a shadow on a wall. Shining the shadow again onto the same wall does not change it. Geometric transformations are matrix rules for images, cameras, and robotics. Rotations use 2x2 or 3x3 matrices. Translation uses homogeneous coordinates, and camera projection divides by depth. Real-world analogy. Geometric transforms are like camera and photo editing tools that rotate, zoom, slide, or flatten the scene. SO3 is the set of valid three-dimensional rotations. The exponential map turns angular velocity into a rotation update, and the logarithm turns a rotation error back into a vector whose norm can be measured. Real-world analogy. SO3 is like a drone's attitude controller. It tracks valid turns without accidentally reflecting the aircraft through a mirror. Orthogonal matrices preserve lengths and angles. Their inverse is just the transpose, which makes PCA, SVD, rotations, and gradient preserving initialization computationally convenient. Real-world analogy. An orthogonal matrix is like rotating a rigid ruler. Distances and angles stay unchanged, and reversing the turn gets you back. Linear algebra for machine learning. Special matrix types and covariance. The library of matrix species opens. Special matrix types are recurring characters with powers. Diagonal matrices scale cleanly. Sparse matrices save memory. Toplets matrices hide convolutions. And covariance matrices reveal how features move together. Diagonal, symmetric, triangular, sparse, block, and low-rank matrices all carry structure. Recognizing the type tells you whether inverse, solve, storage, or multiplication can be cheaper. Real-world analogy. Special matrices are like labeled tools in a workshop. A wrench, saw, and ruler each solve a specific job faster than a generic multi-tool. Positive definite matrices make a bowl-shaped quadratic form. X transpose AX is positive in every non-zero direction. Positive semi-definite matrices allow flat directions but never negative variance. Real-world analogy. Positive definite matrices behave like bowls. Wherever you roll, energy cannot drop below the bottom. Toeplitz matrices are constant along diagonals, which is exactly the structure created by sliding a convolution kernel across an input. This connects CNN filters to matrix multiplication and FFT acceleration. Real-world analogy. Toeplitz matrices are like a window stencil sliding across a signal, reusing the same pattern at each position. A covariance matrix is built from centered data. The diagonal stores variances. Off-diagonal entries store how features move together, and the whole matrix is symmetric positive semi-definite. Real-world analogy. Covariance is like a dance chart showing which dancers move together, apart, or independently. In code, covariance over activations exposes redundancy. The off-diagonal entries can be penalized to encourage decorrelated features, as used in self-supervised learning losses. Real-world analogy. Covariance code is like an audit that spots duplicate gauges on a dashboard measuring the same thing. Linear algebra for machine learning. Eigen decomposition. The Eigen trial asks, which directions does a transformation respect? Eigen ideas grew from vibrations, stability, and differential equations. In machine learning they expose principal components, graph clusters, recurrent stability, and repeated dynamics. An eigenvector keeps its direction when A acts on it. Lambda is the scale. If enough eigenvectors exist, A becomes PDP inverse, meaning change basis, scale independently, and change back. Real-world analogy. An eigenvector is like an arrow printed on stretchy fabric that only gets longer or shorter, not turned. For the 2x2 example, subtract lambda from the diagonal and set the determinant to 0. Solving the quadratic gives eigenvalues 4 and 2. Real-world analogy. Solving the characteristic equation is like tuning a radio until the system's natural stations come through clearly. The eigenvectors are 1, 1 and 1, minus 1, and their dot product is 0. The trace equals the eigenvalue sum, while the determinant equals their product. Real-world analogy. Symmetric matrices give eigenvectors like the main axis of an ellipse, clean perpendicular directions. Eigen decomposition underlies PCA, PageRank, spectral clustering, RNN stability analysis, and fast matrix powers. It tells you what repeated matrix action will do. Real-world analogy. Eigen decomposition is like finding the natural vibration modes of a bridge before predicting how it responds. Linear algebra for machine learning. Singular value decomposition. SVD is the master key because it works even when a matrix is rectangular. It separates input directions, importance scales, and output directions. So compression, denoising, pseudo-inverse, LoRa, and recommender systems all become variations on the same spell. SVD writes A as U sigma V transpose. V transpose rotates inputs into useful directions. Sigma scales by singular values, and U rotates into output space. Keeping only K values gives a rank K approximation. Real-world analogy. SVD is like packing a suitcase by turning clothes, compressing the important stacks, then turning them into the final layout. Singular values can be found from A transpose A in the simple example. Eigenvalues 9 and 4 become singular values 3 and 2. Real-world analogy. Singular values are like measuring the main stretch marks left after a transformation pulls every direction. The code performs truncated SVD. U, S, and V transpose come from NumPy. Keeping the first K singular values compresses a matrix while preserving the strongest structure. Real-world analogy. Truncated SVD works like keeping the loud melody and removing background hiss from a recording. SVD connects many earlier ideas: pseudo-inverse, spectral norm, Frobenius norm, condition number, rank, null space, LoRa, recommender systems, and denoising. Real-world analogy: SVD is the workshop bench where compression, repair, recommendation, and stability checks use the same sorted parts. Linear algebra for machine learning. QR decomposition and Gram-Schmidt. The noisy arrows must be disciplined into clean orthonormal guards. QR exists because solving least squares through normal equations can amplify numerical trouble. Orthogonal directions keep the calculation stable. QR decomposition factors A into Q times R. Q has orthonormal columns, and R stores the upper triangular coefficients needed to rebuild the original columns. Real-world analogy: QR is like turning a messy pile of tent poles into straight support poles plus a simple assembly plan. Gram-Schmidt starts by normalizing the first vector. For the second vector, it subtracts the projection along Q1, leaving a perpendicular component, then normalizes it into Q2. Real-world analogy: Gram-Schmidt is like arranging spotlights so each beam covers new ground instead of shining on the same patch. For least squares, QR avoids forming X transpose X, which can worsen conditioning. With X equals QR, the solve becomes RW equals Q transpose Y, a stable triangular system. Real-world analogy: QR least squares is like balancing a tripod before taking a measurement instead of stacking wobble on wobble. Linear algebra for machine learning. Cholesky decomposition. The positive definite vault opens only to bowl-shaped matrices. Cholesky is fast because it accepts a stricter kind of matrix and rewards that structure with triangular solves instead of expensive inverses. Cholesky works for symmetric positive definite matrices. It factors A as LL transpose, where L is lower triangular with positive diagonal entries. Real-world analogy: Cholesky is like building a stable scaffold from one triangular side and its mirror. In the 2x2 example, write L with unknown entries A, B, and C matching LL transpose to A gives A equals 2, B equals 1, and C equals square root of 2. Real-world analogy: solving the Cholesky entries is like fitting beams one by one so the finished frame matches the blueprint. In code, add a tiny diagonal jitter when a matrix is nearly positive definite. Then factor with Cholesky and solve two triangular systems instead of explicitly forming A inverse. Real-world analogy: adding jitter is like placing a thin shim under a table leg before doing precise work. Linear algebra for machine learning. Jacobian and Hessian matrices. Calculus joins the story. Jacobians explain first-order sensitivity. Hessians explain curvature, and both turn neural networks from black boxes into chains of local linear maps. The Jacobian is a matrix of first derivatives. Rows correspond to outputs, columns correspond to inputs, and each entry says how one output changes when one input moves. Real-world analogy: a Jacobian is like a control panel map showing which knob affects which output gauge. For a neural layer, first compute Z equals Wx plus B. The sigmoid derivative gives one slope per output neuron, so the Jacobian is the diagonal slope matrix times W. Real-world analogy: a neural layer Jacobian is like tracing how pressure through valves changes flow in every pipe. The Hessian is the matrix of second derivatives of a scalar loss. Its eigenvalues classify curvature. Positive means valley, negative means hill, and mixed signs mean saddle. Real-world analogy: a Hessian is like a terrain map that tells whether you are in a valley, on a hilltop, or on a saddle. Full Hessians are too large for modern models. Hessian vector products let algorithms probe curvature, estimate top eigenvalues, and run second-order methods without storing the whole matrix. Real-world analogy: a Hessian vector product is like testing one direction of a mountain trail instead of surveying the whole landscape. Linear algebra for machine learning. Matrix factorization, NMF and ALS. The factorization guild breaks a large table into hidden parts. NMF insists on additive non-negative ingredients for interpretability, while ALS wins by solving one side at a time when the full problem is too tangled. Non-negative matrix factorization writes V approximately as WH, with no negative entries. That makes components interpretable for topics, spectrograms, recommendations, and image parts. Real-world analogy. NMF is like mixing paint from non-negative amounts of base colors. Every part adds something visible. The multiplicative update code rescales H and W by positive ratios. The small epsilon prevents division by 0. Reconstruction is W at H, and the Frobenius norm measures error. Real-world analogy. Multiplicative updates are like adjusting recipe proportions without ever using negative ingredients. Alternating least squares fixes H and solves for W, then fixes W and solves for H. Each step is an ordinary least squares problem, even though the joint factorization is non-convex. Real-world analogy. ALS is like two people assembling shelves. One holds the frame steady while the other tightens screws, then they swap. Linear algebra for machine learning. Frequency domain and Fourier transform. The signal temple reveals that waves are another basis. Fourier analysis exists because time domain signals often hide simple frequency structure. Filters, audio cleanup, image edges, and CNN kernels all borrow this language. The Fourier transform is linear algebra. The DFT matrix F changes coordinates from time samples to frequency coefficients, and the inverse changes them back. The FFT is the fast structured version. Real-world analogy. The Fourier transform is like splitting a chord into individual notes on a soundboard. High-pass filters keep sharp changes such as edges, while low-pass filters smooth noise by averaging neighbors. CNN kernels often learn related edge, texture, and pattern filters. Real-world analogy. High-pass is like outlining the edges of a sketch, while low-pass is like smoothing rough pencil shading. The code shows a Sobel edge detector, sharpening through original minus low pass, and trend removal through high pass filtering. These are signal processing ideas used directly in ML pipelines. Real-world analogy. Frequency tools are like audio equalizer sliders that boost or quiet patterns at different scales. Linear algebra for machine learning. Tensor contractions and advanced operations. The final tower adds axes, batch, time, heads, channels, and features. Tensor contraction is matrix multiplication promoted to many dimensions, and transformer attention becomes the final boss where the whole linear algebra cast appears together. A tensor is an array with more modes. A rollout tensor may store batch, time, and state dimensions, while video tensors add height, width, and channels. Shape names the semantics. Real-world analogy. A tensor is like a labeled warehouse stack. Aisle, shelf, box, item, and time can all be separate axes. Tensor contraction is the general version of matrix multiplication. Paired axes are multiplied and summed away, while unpaired axes remain in the result. Real-world analogy. Tensor contraction is like matching invoices to payments across shared account numbers, then summing each matched set. Ensum labels axes with letters. Letters that vanish after the arrow are summed. Letters that remain after the arrow become output axes. This makes matrix multiplication, dot products, outer products, and attention readable. Real-world analogy. Ensum is like a shipping label that states exactly which axes are matched, kept, or packed away. Tucker and CP decompositions compress tensors. Tucker uses a small core and mode matrices. CP uses a sum of rank 1 outer products. CPALS alternates which factor it solves. Real-world analogy. Tensor decomposition is like folding a bulky map into smaller panels while keeping the important routes readable. The transformer attention equation combines the whole journey. Q, K, and V are learned projections. QK transpose builds pairwise scores. Scaling stabilizes them. Softmax normalizes them, and multiplication by V mixes value vectors. Real-world analogy. Attention is like a meeting room where each word asks every other word who matters most before passing notes onward.